Hello, everyone. We're here now to listen to Federico Bilotti. I'll describe a little bit about who he is, the mechanical staplers and energy devices that are on the market today. Here's Federico. His past starts in '69 in the United States, where he went from Italy to United States to listen to Woodstock. And he was a hippie at that time. Then he became an engineer, worked for a company called Kenner, and designed Star Wars toys. And then when Johnson & Johnson found out who he was and called him to work for J&J, started designing staplers. As you see, the ones circled on the screen are the ones that are still on the market. Today he's a consultant with J&J, Medical Italy, and Eastern Europe for connections with J&J clients. Then I'm also working with surgeons who are inventors and need support to patent their ideas. We're going to talk about bariatric surgery. So in time, things changed and the instrument used became more and more technically complicated. And today we find out through Dr. Sakran, who's one of the group today, that staplers are so critical to cause early leaks with their malfunction. So let's talk about what the malfunction could be. The staples inside the instrument, which is the most important aspect of the instrument, are of two kinds: alloy titanium or pure titanium. Why manufacturers choose one or the other? Manufacturers that use alloy titanium, like Johnson & Johnson, are the ones that have instruments capable to bend those staples because they're the strongest type. As you see in the image, where the blue dots describe the molecules of the titanium and the red dots describe the alloy components, aluminum and vanadium, make the alloy so strong that it's difficult to bend and also to unbend. Instead, the pure titanium at the bottom of the screen, where only titanium molecules are described with the blue dots, are easier to bend and unbend. So the cheap manufacturers, the ones that don't want to build complicated, heavy instruments, are the ones that choose pure titanium. The one like Johnson & Johnson, who have instruments designed for stainless steel staples, because at the time I was director of R&D, I was designing the instruments for staples that were stainless steel. I decided to keep the strength of the instrument and use alloy material. The beauty of alloy material is also the fact that it doesn't have impurities. What are the impurities? One is the fact that they're so strong and they're complicated to assemble by hand. If you push the staples by hand, like you see here on the screen, you get hurt, and the manufacturers who decide to push the staples by hand has issues with that and leaves blood on their staples. As you see, the particles shown on the picture at the bottom, circled in red, are blood stains. From which staples? From the staples assembled by low quality manufacturers. Another benefit of staplers by high quality manufacturers are that the tissue doesn't slip. You see on the left side a red line showing where the tissue is at the time of open instrument, and we're describing linear cutters. And after closing the instrument, the tissue slips out. The slippage of the tissue could be as high as 0.5 centimeter. But if instrument is a high quality, there's anti-slippage aspect, which is the GST that Johnson & Johnson has patented. This is another image of what the tissue does when it slips out. At the bottom, you see that dot tattoo number 8, the tattoo number 9. move forward from open instrument and closed instrument. And the maximum you can move, it's up to half a centimeter. Excuse me for the Russians, and they were invented with one benefit, that staplers that were applying them could adjust their staples heights. The staple heights, I described the reason why height has to be changed. If tissue received the staples without compression, then you would apply 0 gram per millimeter pressure on the tissue. Staples applied at this time would cause bleeding on tissue. If you apply compression of the instrument when you close the instrument, you could apply a pressure that is higher than 8 gram per millimeter square. And then when the staples are formed, if the instrument is designed properly, you can apply 8 gram per millimeter square as described by Russian inventors. And this is what happens to tissue. Why 8 gram per millimeter square was invented? Because suture applied on tissue to stop the bleeding were then tractioned and measured what traction was proper by surgeon. And surgeons know today, by closing their eyes, what the proper pressure is all about. They stop tractioning the suture and the bleeding stops. And even with their eyes closed, they reach that pressure. What is that pressure? Measured by Astafiev in 1969, was 8 gram per millimeter square. And that's how the staples were designed. Now, a manufacturer on the market decided to change the shape of the staples and flatten their surface. By flattening the surface, the pressure applied on the tissue changes. And because of the formula, the simple formula, pressure equal F over A. And if A changes, increases, the pressure decreases. So you don't apply 8 gram per millimeter square, but you apply a lesser pressure. And that's why the design of the staple with flattened surfaces is interesting, how it would keep its shape better than the rounded wire staple. It's true, but not because the staple is better quality, but because the instrument has no ability to maintain the staple formation properly. So let's consider the fact that if the pressure is 8 gram per millimeter square with round wire, then you should make an instrument that is capable of applying those round wire, not cause a reduced pressure just because you can't properly form it. And the blue backgrounds image is one of the top manufacturers today that uses these flattened staple wire. You all know better than I do that the stomach tissue changes from 1.7 millimeter to 3.1 millimeter. So important is to bring the tissue down to a proper height that will allow the staple to close properly. And how does one do that? By waiting 15 seconds. The majority of you does not believe that waiting 15 seconds is important to change the staples at its minimum size, because you're interested in seeing the tissue that doesn't bleed. Sadly, you evaluate the tissue bleeding or not bleeding in acute state during surgery. And certainly the tissue at that time is very elastic. And if you wait or don't wait 15 seconds, you will see no bleeding. So you say, why wait 15 seconds? Why waste my time? What you should then consider the fact that the patient goes home, and if you wait 15 seconds, the patient will go home with open staples, and forever you'll have that staple formation. But the tissue changes, become thinner and thinner and drier and drier. So if there is a possibility of leakage, it will be with a tissue that is compressed improperly because you didn't wait 15 seconds. The tissue could bleed 1 day later. As Sakran noticed, is that there is leakage even 2 or 3 days later. An experiment done on the left side with a cartridge with staples of the same height, and on the right side, staples of different height, showed one important aspect, that if the cartridge is chosen at the right coloration, so blue for intestine, for example, 7 grams per millimeter square is the pressure applied on the tissue, no matter where, along the cut or further inside the patient. 7 grams per millimeter square is the pressure measured, which is extremely low, and close to the 8 grams per millimeter square described by Astafiev and Baker closer in time to where we are today. But on the right side, you have 18 grams per millimeter square pressure applied to the tissue near the cut. And this shows clearly that the tissue doesn't bleed. But why limit yourself to looking at the tissue near the cut? You should also consider the fact that inside the patient, if the staple line inside the patient is bigger and larger, you have lower pressure applied. 3.5 grams per millimeter square is so low that you could have leakage inside the patient, bleeding inside the patient, and you don't notice it because you're only looking at the outside staple line, the only visible staple line. So the decision by gastrectomy experts is to use on the antrum, the green cartridge, and all steps along the intestine, the stomach is blue reloads. And this is what Johnson & Johnson, for example, offers. Blue cartridge at 1.5 millimeter staple height and green cartridge at 2.0 staple height. These are the publications I used to describe the presentation that I just showed you. Let's just jump, for sake of time, I only have 20 minutes for you, that energy devices are also characterized by safe ones and unsafe ones. Interesting the fact that Dr. Sakran described that not only the stapler malfunction could cause leaks, but also tissue ischemia and bleeding could be caused by thermal damage of the gastric tissue. Let's look at the important aspect of energy instruments. All instruments must reach temperatures over 60 degrees or they're unable to coagulate tissue. Thermal footprints is also left by all devices. The question is how large is this footprint, meaning how damaged is the instrument causing laterally to the instrument jaws itself. All instruments require time to cool off. Important is to see how much time does an instrument require. The instruments on the market today should guarantee safety. Interesting is also to look at the water. More water, slower the temperature rise. More compression, less water. Less water, faster seal. Let's look at the physical, biological, surgical aspects that come in play with energy principles. Compression, for example, you all know that you can use compression devices and apply monopolar electrical energy to for the coagulation of the vessel. The coagulation happens in the range of 80 to 150 degrees. Why going beyond the temperature is questionable and also damaging to tissue because carbonization happens. But if you're looking at the tissue to give you the feedback of coagulation and you're waiting for the black tissue to appear, you've gone too far. The carbonization, as we look at beyond this slide, is a symptom of damage of tissue. And that tissue will not be able to support the pressure, blood pressure, or any pressure like tension that the vessel will be applied to. Electricity goes from one polarity to another. And at the bottom of this picture, you see how the tissue starts reacting to it, providing low resistance and attempting to reduce the passage of the electricity. The second part of electricity transfer to tissue, the resistance of the tissue increases up to the time when carbonization, as I described before, causes the electricity to jump around the linear aspects of transition. So no longer from the negative to the red to the positive poles in a straight line, but along the curved lines where the tissue offers less resistance. Collagen and elastin offer two opposite components. One, compressed, keeps the vessel compressed. The other one tries to reopen the vessel. Good energy devices are capable of using the both and keeping the vessel compressed and coagulated. The monopolar staplers, devices, I'm too used to talking about staplers. The monopolar devices can be used at low voltage or high voltage. What is the difference? Well, look at that cut on the tissue. That cut on the tissue can be nice and clean like a scalpel, or can be wide and damaging as the one to the right for high voltage. What is the difference? Is time. In low voltage, the time between discharge electricity is very short. On the right of the image, where you have high voltage, the time between discharge of electricity is relatively larger. And that's why you allow the tissue to relax and then you zap it with electricity. And that damages tissue more. This short video shows how if you press one button or another, you have constant current, or that keeps the light on, or pulsating current, which keeps the light on and off. Coagulating with high voltage turns on the light and then turns off the light. The yellow button will keep the light on. Concentration of current causes damage more than contact to monopolar devices. Where you expect the damage to appear is not the highest damage. Look at what happens where the surface is reduced. You have the disconnection of the tissue. What this means is that you may be unknowingly causing damage to where organs are touching each other in a small surface. There will happen the higher damage than where the monopolar device is touching the organs. How about the indifferent electrode? The negative electrode in contact with the patient should be connected as largely as possible and as widely as possible, because this prevents electricity to run through a reduced surface. And that reduced surface, as I described below previously, can cause damages. Interesting is capacitive pads with substituted the contact pads, because these pads, capacitive, don't work on electricity transfer from patient to the pad, but work on capacitor work to transfer the information that one pad discharges and the other pad recharges, and the information is passed on the generator. It continuously provides electricity to the monopolar device, but the return passage is not done through current through the patient, but is done through a sort of aerial information of the pads with capacitor discharge, which is not transferring electricity, as I said, through the patient. Interesting. Interesting what happened between bipolar and advanced bipolar. Normal bipolar is used oftenly, but doesn't have compression. The heat is the only aspect that provides damage to the tissue and reaches the coagulation the wanted coagulation. The advanced bipolar has compression. That's the main difference. And because of the compression, that can reach higher temperatures, can remove the water from the tissue, it can reach coagulation faster. Here we see on the left, monopolar damage to the tissue, and to the right, the bipolar damage to the tissue. And how the, okay, let's look at that aspect one more time. How the bipolar is causing the electricity to run sideways instead of straight between the jaws of the device. We don't see it because this video is not working. Let's describe this other aspect which is more critical. Ultrasound. This is the damage to the tissue by ultrasound. Certainly different than the carbonized tissue of the monopolar instruments. The ultrasound works differently than any other device because there's no electricity applied to the patient. What the instrument does is apply vibration of one of the two jaws. And this vibration is the mechanical transformation of the electricity that the generator receives, with interesting describing what happens in the handle of the ultrasound device. Piezoelectric rings increase and decrease their volume and their size, and this causes them to bang against each other. This banging is transformed into waves. These waves are mechanical waves and cause the vibration of one of the two jaws. If the instrument is placed next to these waves, you see that the node, which is the value of the wave, is at the crutch of the instrument where the two jaws meet. Then you have no vibration at that time in that site. So you have no coagulation and you have no cutting, but you have the maximum coagulation. Instead, at the tip of the instrument, where the peak of the device, of the vibration happens, the highest vibration possible, then you have the maximum cutting. So be careful about using ultrasound devices as electrical devices, because bipolar devices can be used at the tip of the instrument to coagulate the tissue. So if you have a vessel bleeding, you touch with the tip of a bipolar device and you coagulate it. But if you use an ultrasound device and you touch the bleeding artery with the tip of the ultrasound device, you will cut a hole into the bleeding vessel, because there, the tip of the instrument, you have the highest vibration and the maximum cutting. So use the vessel inside the jaws. Interesting is to look at the ultrasound coagulation process. On the left, we have the compression, and then the H bonds break, and then the denaturation of proteins starts, transforming the tissue into sticky coagulum. The friction, further applied by the vibrating jaw, causes internal tissues to separate and cutting to take place. And so you see that with one unique application of vibration, you first have tissue transformation and then cutting, but in that order all the time. Coagulation first, cutting next. Remember the footprint I told you about? 0.9, Tirelli describes, is the damage to the side of the instrument. 1.3 is the damage to the side of the instruments of a bipolar instrument. So if you have a nerve at 1 millimeter to the ultrasound device, you will not damage it with harmonic energy, ultrasound energy, but you will damage it with bipolar electrical devices. These are some publications that describe how much the ultrasound device is capable of resisting to arterial burst pressure, well, thanks to its inability to bring electricity, which damages the walls of the artery. But the sticky coagulum transforms the tissue of the arterial wall in such a way that these are incredibly strong as a new tissue is created. It's not two walls that are glued together or stuck together as the electricity forces them to do, but it's a way of tissue to be transformed. These are the venous burst pressure. These are the lymphatic sealing mode, always stronger in resisting to internal pressure. This is the damage done to the nerves by ultrasound and bipolar energy. 9.2% is the neural inflammation in ultrasound. 21% is the damage by bipolar. This is the time that it takes by bipolar and the time that it takes by harmonic instruments or ultrasound instruments to cool off. That's 15 seconds. We're getting close to the end. One surgeon during a presentation described to me how important it was to compress the vessel repeatedly, applying electrical energy or ultrasound energy indiscriminately. So either one was not important, but zapping repeatedly with the vessels to reduce the size, because the reduction of its size reduced the pressure that the vessel will leak at. Extremely wrong, because the pressure inside the vessel is the addition of two pressures, a dynamic and a static pressure. By reducing the size, you, yes, reduce the static pressure, but you increase the dynamic pressure. So the addition of the two is always the same. And it's just remembering what you do to water the garden. You squeeze with your thumb, the hose, and the pressure increases, but the static pressure decreases on the vessel. What I say is that the instrument is not as safe because it stops the electrical discharge, but it does it at its own decision when the electricity reaches a certain demand. And this is unsafe as if you driving your car on a highway, reach 120 kilometers per hour, and then you take your safety belts off. And then you wanted to continue driving. This is unsafe. Same happens to this instrument. When you reach a certain electricity demand, the switch turns off, but you want to continue working. And you have to bypass the safety switch and continue without safety. On the left side instead, you see the ultrasound chart. It shows that beeping alerts you on the fact that the instrument took over and decided when the cutting takes place. And it's faster than if you alone continued applying electricity. These are the publications that I read and I use for the publication for the final description that you saw today. Thank you very much. This was all, and I'm sorry about the background noise.